Great job on the exam on Wednesday. I think the mean for the exam was 89 or something. Fantastic. And I don't know how many people, or if there were multiple perfect scores. Like when I write a key for something, I can't even write a key that has a perfect score without some mistake. I don't know how you guys do it. We just have so much stuff to keep track of. Even the simplest mechanism has so many different pathways that you can follow. Right? It's challenging to write mechanisms. So you guys are doing great. Keep up the great work. I realized that first exam was kind of crazy because I'm used to writing exams for graduate level classes. Maybe that was a, yeah, and normally I post previous exams, but I've never taught this class before. So I didn't have any previous exams to give you to take a look at my testing style. So I hope now that you got a sense for my testing style, things will be a little less mysterious about what my exam formats are, and I'm getting more calibrated about what kinds of problems are good to assign. Now we're nearing coming up on the last week of this quarter, and we're not going to have time for me to cover paracyclic reactions in a way that I think would be fitting for the topic. And so I'm going to spend the last 4 lectures talking about phosphorus, organophosphorus chemistry, and organosulfur chemistry, which we have been seeing from the very beginning of the quarter, but kind of sidestepping it and not really talking about it, and it doesn't get covered to a sufficient extent in any normal organic chemistry class that I've ever seen offered at any institution. So let's go ahead and talk in detail about how to think about the chemistry of phosphorus and the chemistry of sulfur. It's like these second row atoms over here, boron, carbon, nitrogen, oxygen, maybe some silicon is super important. We've been talking about that from the get-go, so I hope you guys are used to seeing beta-silyl carbenium ions and substitution at silicon. And so now let's dig into these other third row atoms, phosphorus and sulfur. So I want to introduce you to some nomenclature here because I'm going to be using terms and you'll be wondering what I'm talking about. And we need to be on the same page with some simple types of nomenclature. I've shown here some common phosphorus functional groups. And so let's go ahead and talk about the names for these. What are some of the common ones here? Well, one of the most common types of phosphorus functional groups that you're going to see in an organic chemistry class is a phosphine. And the key here is that there's a lone pair on this phosphorus atom. Let me go ahead and draw that lone pair here on phosphorus. There we go. That's distinctive. And by far the most common phosphine that you're going to see is triphenylphosphine. We'll talk about that shortly. It's the most common phosphine reagent that's used in organic chemistry labs, probably in, maybe in organometallic chemistry, depending on which metals you're looking at. So another common phosphorus reagent that you're going to see that has a lone pair on there is called a phosphite. A phosphite. And I'm not going to draw out the acid version. This is actually a phosphite ester. And there's an acid called phosphorus acid that you almost never see people use. That would be with OHs on there. It's called phosphorus acid. But this species right here is called a phosphite ester. It's another common type of reagent that we're going to see in these lectures and that you use in an organic chemistry lab and sometimes as ligands for transition metals. All of these are going to be classified by oxidation state as phosphorus 3 functional groups. Phosphorus 3. And it depends on how many atoms are attached to phosphorus that are more electronegative than phosphorus. Turns out carbon is more electronegative than phosphorus, so we call these phosphorus 3. Whether you have 3 bonds to chlorine, 3 bonds to oxygen, 3 bonds to carbon, these are all phosphorus in the oxidation state of 3. There's a couple more functional groups here where you have mixtures of alkyl groups and oxygen groups, or mixtures of alkyl groups and chlorine. These are not so common. Phosphinite, where you have 1 alkoxy, phosphonites, where you have 2 alkoxy groups. Those are less common intermediates. You'll see them. But by far, 3 alkyl groups, 3 phenyl groups, or else 3 oxygens. Those are the most common phosphorus 3 types of functional groups that you will see in organic chemical reactions. Well, let's step down and take a look at this beautiful looking bond right here. P double bond O. Man, that is awesome. You know, I've talked a lot about how C double bond O is a driving force. Carbon dioxide, you burn things, you end up with carbon dioxide, 2 C double bond O's. That's a major driving force in organic chemistry. Look at all these compounds down here that have 5 bonds to phosphorus. So with these 5 bonds to phosphorus, all of these functional groups are in the oxidation state of phosphorus 5. So these are all phosphorus 5 compounds down below with this P double bond O. And you could have other P double bond something, P double bond carbon, that's a Wittig reagent. You should have seen before, we'll talk more about those. P double bond N, less common, but it's P double bond O, that's where nature wants to be. Everything you do is going to funnel toward some P double bond O. It'll keep reacting with air, water in the air, whatever, until it gets to P double bond O at the end of your reaction. So what are the common phosphorus 5 functional groups? Well, by far the most common phosphorus 5 functional group that you're going to see is a phosphate or a phosphate ester. Now, there is something called phosphoric acid where you have OHs on there. We just don't use that very often. It's like, why use phosphoric acid? It's not as strong as sulfuric acid. It's not, I mean, people just don't use it. It's not got any advantage over sulfuric acid, which is inexpensive to form. So we won't really talk about phosphorus acid, phosphorus 3, or phosphoric acid, but the esters are common. Why are they common? Because that's the main stuff of biology. So if you've taken any biosci class in high school or anywhere else, DNA, RNA, phosphorylated proteins, ATP, that's all phosphorus 5 chemistry. They're all esters of phosphate. And so a geneticist may never draw out that phosphate ester group. They'll just think at the level of A, G, C, and T, but that's all connected together with phosphate groups. There's one other common functional group that you'll see that is completely worthless, but it's the endpoint of most reactions, and that's phosphine oxides, where we have an alkyl groups here on phosphorus, and then you got that amazing P double bond O right here, so stable. Once you get there, there's not a lot you can do with that. That's trash. You're going to throw that in the trash, in the organic waste, usually. You can get the double bond O off. You got to find a more stable bond or trade it off, silicon reagents to strip off a silicon oxygen, but that's usually the end point. And you're not going to usually use that as a starting material in organic chemistry. Now I've got one more type of phosphorus functional group that you need to know that is the key one for all of this chemistry that we're going to be showing you. And I'm going to be showing you this over and over again. And it's an intermediate called a phosphorane intermediate. You could, in special cases, make stable examples where there's all single bonds to phosphorus 5. But usually these are so unstable, you're just generating it as an intermediate when you're doing substitution. Kind of like tetrahedral intermediates are important when you substitute acyl chlorides or esters. We're going to be drawing a lot of phosphorane intermediates, trigonal bipyramidal structures where the electronegative atoms, the nucleophile and the electrophile, are at axial positions. We're going to be drawing these over and over. So if you want to understand substitution of phosphorus 3, how to replace those groups, if you want to understand substitution of phosphorus 5, those phosphorane intermediates are essential. Get used to drawing 5 bonds to phosphorus. This is not carbon. 5 bonds to phosphorus is no problem for phosphorus. We're going to be doing most of our substitution reactions through phosphorane intermediates that have 5 single bonds to phosphorus. Now I mentioned this P double bond O. It's like, look at that, everything is heading towards this type of phosphine oxide intermediate where you have this P double bond O there, right? There's an immense driving force where if you want to drive an organic reaction, you want to drive towards formation of P double bond O. And we've talked about C double bond O as a driving force, carbonyl groups. Organic reactions that trade off C double bond C, and there's lots of those, for C double bond O are going to be thermodynamically favorable. That doesn't mean that they're fast, that's a kinetic barrier, but you can go downhill in energy and have favorable products if you generate C double bond O. And you'll often see in cases like this where you trade off CC double bonds in sigmatropic rearrangements or some of the other reactions that we've seen, you benefit here. It's like a 30 kcal per mole benefit in energy. You're going downhill, making a more stable C double bond O if you form carbonyl groups. And we're going to see a similar theme here with phosphorus chemistry, right? Usually at the end of your reaction, when you do phosphorus chemistry, we're going to generate P double bond O. So how much more favorable is that? Is it 30 kcals? Well, let's look at the starting material. Sorry, I don't have the numbers for triphenylphosphine or trialkylphosphine, but I have the numbers here for what does it take, well, how much energy do you benefit if you go from trichlorophosphine, PCl3, phosphorus trichloride, to phosphorus oxychloride? Well, it's 110 kcals per mole for this double bond O in in phosphorus oxychloride. But if you look at the starting material here for that oxidation, there's no bond there. And so you're starting off with something that has 0 bond and 0 kcals per mole, and you end up with something that's 110 kcals per mole. That's insane. Like 110 kcals per mole more stable in energy. Boy, a carbonyl is nothing compared to that. So you're going to see lots of reactions where you start with P with a lone pair and you end up with P double bond O at the end. And there's no problem for a driving force for the products to be more stable than the reactants if you're forming P double bond O. So look for P double bond O as a byproduct in a lot of these reactions we're going to see. Okay, so get ready to draw substitution reactions and other types of processes that go through these phosphorane intermediates, these things that are going to freak you out at first because there's 5 single bonds to phosphorus, because you're still probably thinking like carbon, but no problem with phosphorus. Get used to this. You'll start to see them over and over and over again. Now let's go ahead and talk about the relative reactivity of phosphines. So phosphines are with 3 alkyl groups, or usually 3 phenyl groups on phosphorus, are more common than phosphites with oxygen substituents or chlorine substituents. And so let's go ahead and take a look at some relative rates as I change the substituents on these phosphorus atoms. So if I take some sort of a phosphorus nucleophile, there's a lone pair on that phosphorus, and we think about how fast does that do some sort of an addition reaction? How good of a nucleophile are these as I change the R groups on the phosphorus? And let me go ahead and give you some numbers here that have been measured in the lab. I don't think I acknowledged them here. This came out of Herbert Meyer's website with Armin Ophiel. And they took the time to measure these detailed rates for these types of addition reactions. So I'm going to go ahead and assign a relative rate here of 1 for triphenylphosphine. That's the most common phosphorus 3 reagent that we have in any organic chemistry laboratory here at UCI or in most places. When you replace the phosphine groups with alkyl groups, you might think that the alkyl phosphines are more standard. They are more reactive. And I'm not giving you an appreciation for how much more reactive trialkyl phosphines are, because I picked a very specific addition reaction for addition of phosphines to enones. But if you go into the laboratory and you just open up a bottle of trialkyl phosphine, it immediately starts to oxidize on exposure to air. Organic chemists don't like to work with trialkyl phosphines because you have to work with them in a glove box or be super quick because they are unstable to air. And so you'll find that these that trialkyl phosphines, like tributylphosphine, they oxidize more, somewhere on the order of about 100 times faster. I'll just put oxidation here. So, for this addition reaction, 5 times faster, but you can get up to 100 times faster, maybe more in most reactions. Generally, trialkyl phosphines are more nucleophilic than triphenylphosphine. And it's the same if I put cyclohexyl groups on there. If you're thinking this is a steric thing, that's not why the tributylphosphine is more reactive. So you can kind of see, oh yeah, maybe there's a little bit of resonance that's deactivating that lone pair. I think you're starting to get why the triphenylphosphine is less reactive than trialkyl. Now, when you put oxygen substituents on phosphorus, those oxygen lone pairs have 2 types of effects, but the main effect here is that oxygen is electronegative. And because these oxygens are electronegative, this phosphite ester that I've drawn here, this phosphite, is less reactive, 1,000 times less reactive than the triphenylphosphine. Well, let me do that in red, just so my colors match. 1,000 times less reactive. So if I'm just looking for nucleophilic power, I wouldn't choose the phosphite. There's other reasons to choose phosphites. And then the best reason is it's already got the PO bonds that it loves, but those lone pairs are less reactive. Now, we haven't had a lot of experience with phosphines as nucleophiles so far, but what you have had experience with is nitrogen lone pairs. And so let's try to compare these rates to those with nitrogen lone pairs. If I compare triethylphosphine with triethylamine down below, or I compared tributylphosphine with tributylamine, the alkyl group identity doesn't matter that much. Let's just go ahead and take triethylamine as an example. The relative nucleophilicity in this conjugate addition reaction on top is that the amines react faster, 72 times faster in this type of conjugate addition reaction that I drew here on the top of the page. So is a factor of 72 versus 5 that meaningful? Maybe not so much. But look at what happens when I put a single phenyl group on the nitrogen. If I move over here and just put one phenyl group, like how do I tell which is more nucleophilic? Is it triphenylphosphine or is it triphenylamine? Now, unfortunately, I've never seen, and I've seen a lot of chemistry, I've never seen anybody work with triphenylamine and try to get a lone pair to add to anything, ever, in my whole career in chemistry. Let's talk about what happens when you put a single phenyl group on an amine. You just kill the reactivity. You kill the reactivity over here when you put a single phenyl group on the amine, and that's because, as you might guess, that's because the lone pairs are donating into the benzene ring. You already know that. You know that the benzene rings of anilines are super reactive in electrophilic aromatic substitution. That's where the nucleophilicity is. It's in the benzene ring. You got nice regular length bonds, nitrogen to carbon. So that resonance is quite powerful at deactivating. That's 0.06 that I meant to draw here. Now, and if you put 3 phenyl groups on an amine, I have no idea what that is. Nobody's ever used that nitrogen lone pair as a nucleophile, but I can tell you for sure it is less, way less. I shouldn't put I don't mean to put equal. It's not less than equal. It's way less is what I mean to draw. Way, way less than 0.06, which is the number for a single phenyl group. So if you put even one phenyl group on an amine, you're really deactivating the amine. And if you put 2 phenyl groups, it's over. It's over for the, yeah.
For the trialkylphosphines, or actually just like comparing the amines and the phosphines, is the phosphine more selective for conjugate addition, or does it also do 1,2 addition?
You'll never know whether the phosphine does 1,2 addition, because the phosphine can do 1,2 addition, but it'll get pushed right back out. So I don't know what the rates are, and we could probably determine that. But the general expectation is that phosphines add faster 1,4 addition. They add faster to this end, but you're never going to know how fast it adds to the carbonyl because it gets pushed right back out. Yeah.
So would that like whereas like the cyanide anion and like when they cool down the solution and it's like, oh, because one is reversible and the other is not, that it just turns it all into like.
Yeah, I haven't framed our discussions in this class in terms of a principle called hard-soft acid-base. And I set up this class talking about, at the very beginning of the class, I set up this class talking about the importance of MO diagrams and how you can use the energies of filled and unfilled orbitals, let me just draw it like this, of filled and unfilled orbitals to make guesses about which things are easy to attack and which things are not. Generally, what you would say is that the unfilled orbital of a CO is not as low as the unfilled orbital of the enone. And so there are many reactions where the main driving force is addition to the lowest energy orbital. And so, for example, phosphines, sulfur, enamines tend to go for the lowest energy MO. But there's other reagents like cyanide that you mentioned that will attack the carbonyl faster because it's more interested in charge. Oxygen has a lot of negative charge. It loves the charge of the carbonyl more. And we didn't talk a lot about these special cases where you have to think about the difference between charge-driven reactions versus low LUMO-driven reactions. So let's just set that aside for now. There are some reagents that prefer to attack the carbonyl faster. They're mainly ones where there's a lot of negative charge on that nucleophilic atom. Fluoride, anion, oxygen, anion. So things with a lot of negative charge will go after the CO faster than the enone end. But phosphines, boy, they love this end here, man. Look at that. They love Michael additions. We mentioned that before when we talked about conjugate addition reactions. All right, let's go ahead and talk about our first reaction here using a lone pair on phosphorus. Let's get ready. This is an ancient reaction. I don't know how ancient. A century old, maybe more, probably more than a century old, called the Michaelis-Arbuzov reaction, sometimes called the Arbuzov reaction. And it starts here with this phosphorus lone pair on this phosphite. Now, phosphites aren't that reactive. This is a phosphite ester, triethyl phosphite. It's probably one of the cheapest phosphite esters. And, it's not as nucleophilic as triphenylphosphine. So they have to heat this. They're heating this reaction up. Phosphite esters aren't that reactive, but you heat it, and you can get SN2 reactions to go. Now, this is no normal SN2 reaction, putting a leaving group next to a carbonyl makes it easier to attack. So we're cheating a little bit, but you still have to heat it. And when you heat this up, you can get this phosphide ester to do an SN2 on a great SN2 substrate. There's no beta hydrogen, so you can't do elimination reactions. But all this can do is SN2. And this is going to make an intermediate that now has four bonds to the phosphorus. So let's go ahead and draw out that intermediate here. So we got phosphorus. Let me go ahead and draw out these three oxygen groups on here. We've got 4 substituents. We need to end up with a positive charge on here. And after I do the SN2, right, I now have a phosphorus carbon bond. And we've got these 3 ethyl groups, these ethoxy groups. And because I've seen this mechanism over and over and over, I know I'm smart enough to draw one of those ethyl groups where I can see the carbon-oxygen bond. Boy, do I want to generate a P double bond O. Somehow, some way, I want to generate P double bond O. Look at this. Boy, you want to generate that because that's really going to be the driving force here. And so now I'm going to use this bromide anion, not a great nucleophile. I'm going to use that bromide anion I got from the SN2, and I'm going to come back and around, and I'm going to attack that ethyl group. I'm going to do an SN2 on the ethyl group, which is not great, but look, I get to make P double bond O out of that. If I attack the carbon atom, I get to make a P double bond O act as a leaving group. You're going to see this over and over and over again. Reactions driven by the formation of that P double bond O, whether it's DNA or, well, all of biology, it starts with phosphorus 5. That's a little bit different. Okay, so this is a powerful process for making phosphinate esters. I'm pretty sure if you took the organic chemistry laboratories here in the Chem 51LC series, you did a Wittig type reaction with exactly this reagent. Might have been called a Horner-Wadsworth Amines, or they might have called it a Wittig reaction. But these are commonly used as reagents for doing olefination reactions, kind of like Wittig reagents. Okay, so P double bond O, just awesome there. Let's go ahead and take a look at some more processes. This one is going to look so strange to you. Boy, people love to trip you up with your inability to write out the mechanism for this reaction. It's like if you get into some sort of oral exam, they'll draw this out and they'll be wringing their hands and going, they're never going to get this. Because there's so much strange stuff going on here, and it starts off with the first step. So when you took an introductory organic chemistry class, you learned how to take alcohols like this and convert them into carbon-bromine bonds using PBr3. That's not that common. I mean, if I think about all the reactions I've seen people in our department do to make carbon-bromine bonds from alcohols, they didn't use PBr3. They used this reaction called the Appel reaction. Let's go ahead and take a look at how this Appel reaction works. And the first step is going to kill you. It'll be like, what's going on here? You know, we do want to generate P double bond O at the end of the reaction, but the first step you're never going to get. So I'll draw it out for you. See this lone pair on phosphorus? We're going to use that, triphenylphosphine. And the thing that you never could have guessed is that we're going to attack this carbon tetrabromide, and we're going to do an SN2 displacement. Like this. How many of you would have guessed that we were going to attack the bromine atom? Never in a million years you would have attacked the bromine. And if you haven't seen this, and if I didn't make a big deal about it, you'd forget it. So now I'm just going to make a big deal about that. You attack the bromine. You attack bromine, not carbon. Yes, I know bromide is what you were told is a good leaving group, but the LUMO is lowest on the end of that bromine atom. Boy, who would have guessed that? Let's go ahead and draw out the intermediate you get here. Isn't that crazy? And now we get this phosphonium intermediate, just kind of like an ammonium, 4 bonds to phosphorus. You better have a positive charge on there. Look at that phosphonium intermediate right there. Now, at the same time that you do this, you generate this anion. Who would have guessed that this might be stable enough as an anion to act as a leaving group? You couldn't have guessed that. I have to tell you that. In fact, there's quite a few reactions where trichloromethyl anion, tribromomethyl anion, triiodomethyl anion acts as a leaving group. Breaking carbon-carbon bonds, like what business does it have to do that? And if you look at that anion right there, it's about as stable as an enolate anion. I've got some pKa's written down for you here. Like if you take iodoform, that's the name of this molecule, triiodomethane is called iodoform. That's got a pKa like an alpha proton next to a carbonyl. Bromoform is about the same. It's got a pK about the same as a proton next to a carbonyl. Chloroform, a super common solvent in organic chemistry. It's got a pK about the same as a proton next to a carbonyl. So it's not crazy to have these carbanions. It's not crazy to have enolates. It's not crazy to have a bromoform anion, but you never could have guessed that this reaction would start off by attack on the bromine. And about a month from now, you're going to forget this, and you'll never be able to draw out the mechanism again. So don't forget it. Trust me, you're going to forget it. You're going to forget to attack the bromine because we're fighting against a whole year of mistraining in introductory organic chemistry. Now that bromoform anion does want to pick up a proton, so you shouldn't be that surprised that it can deprotonate this alcohol like that. That shouldn't be a surprise to you. And what that does is it generates this alkoxide that's quite nucleophilic. Let's go ahead and draw out these species here. You get this alkoxide that's nucleophilic, and it's going to come back and add in to our phosphonium ion. Man, I've got the O- and I've got phosphorus. Don't you feel like you want to form a phosphorus oxygen bond? We got to get to P double bond O. Phosphorus loves oxygen. Boy, you don't have to guess what's going to happen here. I got to get to P double bond O somehow. So let's go ahead and use this O- over here to attack that phosphonium group. And let me be a little bit more specific here, even though we don't have to do this. I'm going to show that it attacks the backside. Opposite. It comes in from the opposite side of the bromine atom. And we're going to generate this phosphorane intermediate with 5 bonds to phosphorus. Don't freak out about this. We're going to see a bunch of reactions that proceed through phosphorane intermediates. And so let me draw the 2 electronegative groups here. I'll put the bromine atom on the bottom here. And opposite that, in our trigonal bipyramidal structure, I'm going to put this alkoxide or alkoxy group. And over here in these equatorial positions, I've got these phenyl groups. I've got these long bonds axial. Boy, something wants to act as a leaving group here. I kind of only have 2 choices. One of these is going to act as a leaving group, either the bromide or the alkoxide. Well, that's an easy decision. What's going to act as the leaving group here? I got a couple of ways to depict this, but I'm just going to use the bromide just leaving on its own without using lone pairs or doing anything to push it out. And this is going to bring us back to a phosphonium ion. Right? We had a phosphonium ion over here, then we made a phosphorane, and now we're going to go back to a phosphonium ion by kicking out a leaving group. And this is a pattern you will see over and over again. So now I've got my phosphorus here. It's a phosphonium ion. Let me put those 3, and it's now tetrahedral again. And I got this allyl group there. Boy, do I want to form a P double bond O. Man, I want to form P double bond O. And if you're thinking, well, shouldn't I have drawn the lone pairs over here pushing out? That you could have done that if you wanted. I'm just drawing a different resonance representation. But we've still got that bromide floating around here, and I'm going to make that bromide float around up here above that carbon. And this is now going to look kind of like that Arbuzov process. We're going to attack the carbon atom. Can you attack the phosphorus? Yeah, that'll take you backwards. We're not going backwards. Yes, you could attack the phosphorus, but every once in a while you attack the carbon. And if you attack the carbon, that's really a poorly drawn lone pair right there. Now we break this, and I'm going to give these electrons, let me do it in red. There we go. Yeah, we do form a bromine carbon bond, but the main point is we get P double bond O out of this, right? Okay, so this is an Appel reaction. This is the way most people, if I go to some organic chemist in our department, say, oh, you got to turn this alcohol into a bromide. This is what they would use, not PBr3. Yeah.
I know this doesn't happen in situ. So, for example, when the oxygen pairs itself with the phosphorus, why does the bromide not leave at the same time?
So let me see if I understand the question. Is the question, why doesn't this push out the bromide?
The step before that.
The step before that. How do we know that this is not SN2?
Yeah, pretty much.
Yeah, because we are not at any point going to do SN2 reactions on these types of phosphonium ions.
So the phosphorus is comfortable having less.
well, there's no formal +2 charge on here. It's very happy having 5 bonds. The question you're asking is kind of like this question. How do we know that this is not an SN2? Right? How do we know that this doesn't go through an SN2 reaction? It's the same kind of deal. It's like it could in theory, but the LUMO, the empty orbital, yeah, you just stop at the phosphorane. Somebody has to tell you that it always stops at this intermediate. That's an intermediate in these substitution reactions. It's an intermediate when you form bonds in DNA. In RNA, you go through these intermediates where there's 5 bonds, 5 single bonds to phosphorus. And somebody has to tell you that it goes to that, because you couldn't know. You couldn't know that it doesn't do SN2. There was no way to know that from any principle that we've taught you in this class so far. Yeah, so it's a good question. It's like, this is where I have to get you used to seeing these phosphorine intermediates with 5 single bonds to phosphorus. Okay, boy, we're really going to we're going hardcore. This is like the hardest, I think this is the hardest mechanism we've got in this lecture. We're going to have lots of mechanisms on phosphorus. And this is a common reaction that's used in organic synthesis. When people make a mistake and they want to try to fix their mistake using organic synthesis, there's lots of cases in organic chemistry where you have one configuration of alcohol. Maybe you didn't do the sodium borohydride selectively, or there was some other aldol addition that gave you the wrong stereochemistry, and you want to invert that so that the oxygen is pointing downward. So usually we use this Mitsunobu reaction to invert the stereochemistry, and then they hydrolyze the ester in a second step and hope nobody noticed that they're trying to fix a mistake. So Mitsunobu reactions are great for inversion of alcohols. The product is not really an alcohol, it's an ester, but you can easily hydrolyze esters with sodium hydroxide. And the reagents that you use for this are triphenylphosphine and DEAD. Now you know what triphenylphosphine is. I'll go ahead and explain to you what is DEAD. Nobody says diethyl azo dicarboxylate. They just call it DEAD. And so let's go ahead and draw out the mechanism for this process. And the mechanism is going to involve, you can kind of see what's coming here. The mechanism is going to involve making a leaving group that looks like triphenylphosphine oxide. Right? We're going to use this as a leaving, and our driving force for making that new carbon-oxygen bond is that we're going to generate a phosphine oxide as the leaving group. Doesn't it always seem like all our reactions involve that? That's right. Okay, here's DEAD. It's diethyl azo dicarboxylate. This is an azo linkage right here, this N double bond N. If you took an introductory class in organic chemistry, you probably learned how to make diazonium groups and do electrophilic aromatic substitution to end up with 2 phenols with an azo linkage in between. Almost every colored food that you eat, Cheetos, Doritos, or that drink, is made out of dyes with these azo linkages. That's why they teach you that in introductory organic chemistry. This is weird because it's not 2 phenyl groups on the azo, it's 2 esters. And when I see this, what I see is, oh man, conjugate addition. I want to add to that N double bond N because it's got all this conjugation here with these 2 carbonyls. And because it's nitrogen, replacing carbon with nitrogen lowers the energies of the LUMO. This is a hot low LUMO acceptor. And so let's go ahead and walk through what happens. We're going to do conjugate addition here, and I've got my lone pairs on phosphorus, and I've got my low LUMO enone here, except it's got an NN double bond that is weak NN double bond, and I'm going to do this. I'm going to take these electrons. I could have added to either nitrogen. I'm just drawing it, adding to the nitrogen over there on the right-hand side. We're going to do a conjugate addition reaction. And so you can see that I've put the negative charge over here in this nitrogen. I could have pushed the electrons all the way into the carbonyl. I'm just choosing to stop here. Now you've got this kind of amide anion. The real term would be a carbamate anion, but it doesn't matter what you call it. I've got N minus, and I want to end up putting a proton on there. Let me go ahead and draw the lone pairs. You know, there's an equivalent of carboxylic acid floating around. You know, it's not easy to protonate triphenylphosphine. Triphenylphosphine is not like triethylamine, but the N minus does want to pick up that proton. And so let's go ahead and deprotonate that carboxylic acid that's been floating around in there. And now when we do that, we generate a carboxylate anion, and that's going to end up being our nucleophile. I'm not going to draw that carboxylate anion now. I will later. And so what we've generated now is this phosphonium intermediate with a phosphorus-nitrogen bond. phosphonium with a phosphorus-nitrogen bond. Look at that. Man, I don't want phosphorus nitrogen. We want phosphorus oxygen. We want P double bond O. We got to figure out some way to make P double. So now this is a good time for our alcohol to come in. Could the carboxylate come in? Yes, but that doesn't lead you in a productive direction. And so every once in a while, the alcohol will come in and add to that phosphonium. And you'll end up with a phosphorane intermediate, like this. See this phosphorane? 5 single bonds to phosphorus. And our nucleophile and our ultimate leaving group are at axial positions. And when we do this, right, now we're prepared to use a basic species. I'm going to draw it as the conjugate base here. I'll just draw A minus here. You can pull that proton off. I'm just going to pull that proton off. And once I pull that proton off, now I can go back and put it on that nitrogen on the top. I want to pick up the proton on the oxonium and put it on that nitrogen on the top because I want to make that nitrogen act as my leaving group. So I want to pick up this proton here and I want to put it over here. So let me go ahead and draw out this nitrogen that's going to act as a leaving group eventually. Let's go ahead and protonate that. And you might argue whether the proton goes on the nitrogen or whether it goes on the carbonyl oxygen next door. I'm going to depict it like this. Let me draw that in black, just the arrows red here. So I'll go ahead and draw this, H, A. Now we'll put that same proton back on the nitrogen, and so now it's ready to act as a leaving group. So now we're ready to make this act as a leaving group, and I'll just pick up these electrons and I will push them out. Now yes, you could have drawn the mechanism by using the lone pairs on oxygen down here to push out. That's fine, it's just a different resonance representation for the same reaction. I'm going to draw it as this phosphonium intermediate, and now I just really want to make a phosphine oxide out of this. Unfortunately, we still have floating around some of our carboxylate. Our carboxylate species is still floating around here. Let me go ahead and draw out some of that carboxylate species. I've still got this carboxylate that I've thrown in here. You could use any acid you want in this reaction. I drew it as an arrow. And so that's now going to do an SN2. Can it attack the phosphorus? Yes. It's not going to lead you to the product. If you're thinking, oh man, I really want to attack this phosphorus, you're not crazy. Actually, it would attack backside here. That's not crazy, but that's not going to lead you to the product. Every once in a while, after you get tired of attacking the phosphorus, you're going to end up doing an SN2 reaction. Kind of like we did with bromide, attacking the carbon, or right, it's the same thing. Eventually you're going to attack carbon. Yes, you could attack P+, that won't lead you anywhere, but every once in a while you're going to attack carbon and then make phosphine oxide act as a leaving group. So the end result in this reaction, the Mitsunobu inversion reaction, is that we end up, because we did an SN2, we've inverted the stereochemistry. We start off with one carbon-oxygen bond, and we replace it with a different carbon-oxygen bond by doing an SN2. And once again, we're using triphenylphosphine oxide as a leaving group. Man, this is a long, crazy mechanism with big things in here. Kind of painful to write out, but I expect you to know this. Expect you to know the Appel reaction. You know, the main theme here, I don't feel like this is as hard as the Appel reaction. I feel like this step here is easier to see than that attack on that bromine in the bromoform, personally. But it does have all these big structures and seems kind of long. And if you tell anybody you've had electron phosphorus chemistry and you didn't learn the Mitsunobu reaction, they think, what the heck is that about? Yeah. Yeah, so the question is does this suffer from the other problems that SN2s suck? Yes, yeah, it does. You're lucky that this works on secondary alcohols. Tertiary, no chance. You just go through SN1 ionization to make carbenium ions. And for some reason, you can get away with decent yields, not perfect yields, 80% yields, not 100% yield, 80% yields. And you're always worried about in any SN2 process, this alternative elimination reaction. It's always an issue. Are you going to see competitive elimination, which is irreversible? So You usually don't get 100% yields, but it works well enough on secondary alcohols that are chiral that you can get away with this. But any SN2 reaction is not great. And let me just come back and let's marvel at how set up we were over here. Notice how I couldn't do an elimination here because making an alene, right? You typically you want to apply these reactions where there is no way to do an elimination. So the Mitsunobu you can kind of get away with SN2 without too much elimination to kill your yields. Okay, let's talk about substitution of phosphorus, right? If you were some deity trying to design chemistry and biochemistry, how would you substitute phosphorus? If you had leaving groups on phosphorus, any kind of a leaving group, could be chlorides here, could be bromides here, could be oxygen here, and you wanted to substitute those for something else, how do you expect those to work? And I want to point out a fundamental difference between how easy is it to attack at phosphorus when there's a lone pair versus when there's that oxo group on there. And you can make the generalization that if you compare phosphorus 3 phosphites versus phosphorus 5 phosphates, it is faster to substitute. It is always faster to substitute when you have the lone pair. It is slower to substitute when you have P double bond O. So if you have a nucleophile, if you're under nucleophilic conditions and there's nothing acidic going on, right, it's faster to substitute phosphites. If you had to make a choice on how you were going to make a PO bond, you would use a phosphite. But I want you to look down at the row below where under acidic conditions, it's a slightly different order of magnitude here. It's not just 1,000 times faster. It is now 1 billion times faster when we're talking about acids. Don't you wish you could get your bachelor's degree 1 billion times faster or finish your homework 1 billion times faster? Right? 1 billion times faster. If you have to make a choice for what kind of chemistry you're going to do in a lab to substitute phosphorus, let me recommend that you try to use acidic conditions. Right? If you want things to work well and fast, 1 billion times better, do things under acidic conditions, and let's take a look at why. Yeah? Yeah, we'll come back to that. The question is, okay, acidic conditions sound great, but doesn't that mean your products aren't going to be stable under the acidic conditions? We'll come back to that, yeah. Okay, so let's go ahead and take a look at the mechanism for why is this so much faster? What on earth is going on with this? It's not just a million, it's not 1 billion. I've got this, I hope I have this right. I thought it may be 1 trillion times fast. You know, who cares? Is it 1 billion or 1 trillion? It doesn't even matter. I don't even remember. It may be 1 trillion, and I've got this wrong. Let's take a look at the mechanism for substitution with chloride. If you substitute PBr3, it's a reagent you should have seen before if you've taken a sophomore organic chemistry class. And if you want to substitute bromine for chlorine under acidic conditions with HCl, what's the mechanism? Well, the mechanism is going to start off with attack of phosphorus on that proton. You're going to protonate the phosphorus. And when we do this, we're going to generate a phosphonium intermediate. Phosphorus with 4 bonds, that's a phosphonium ion intermediate. Let's go ahead and draw out that phosphonium ion intermediate. And as soon as we generate this phosphonium ion intermediate, I feel like I want to attack it to make a phosphorane with 5 single bonds. So P+, now that we've put a proton on there, and you don't get this with carbon or second row atom chemistry. So now that I've protonated that, now it's very easy to make a second bond to the phosphorus. You add the electrophile, the proton to the phosphorus, and now we're going to add a nucleophile to the same atom, to that phosphorus atom. So let's go ahead and use that chloride anion to come in and attack. I still got chloride around here. There it is. And it's going to come in and attack from opposite the electronegative leaving group. I'm going to use a red arrow there. Now I have 5 bonds to phosphorus. We're making a phosphorane intermediate like we've been doing over and over and over again. We'll keep doing it. I've got this phosphorane intermediate. Here's my leaving group. Here's my nucleophile, electronegative atoms. Whoops, no negative on the chloride anymore. There's no charge on the phosphorus. Phosphorus 5, phosphoranes, neutral phosphorus. Just because it's neutral doesn't mean it's stable. I got great leaving groups here. You could push out the chloride. That'll happen, but it's going to just take you backwards. But sometimes you push out the bromide. Whoops, I didn't mean to erase that. And that'll take us back to a phosphonium intermediate. Well, let's take a look at that phosphonium intermediate. Zillions of times faster than any other mechanism you could draw. And now we're going to pull off the proton. So I've got some sort of an A minus, Br minus, Cl minus, who cares what it is, and we just deprotonate that phosphonium. This may seem like a long drawn out mechanism to you, but this is why substitution under acidic conditions is zillions of times faster. Billion, trillion, I don't know, zillions of times faster. If you're not drawing this mechanism, you're missing out on something, if there's any hint of acid. So let's go ahead and take a look at a reaction that you should have seen before that involves exactly this kind of substitution. So if you've taken an introductory class in organic chemistry out of a standard textbook, they'll draw some stupid misguided mechanism that looks like an SN2 on phosphorus bromine bonds. And that's not how it works. Let's go talk about how these reactions work. So hopefully you've seen this reaction of phosphorus tribromide, PBr3, converting alcohols into carbon bromine bonds. You were told this is a great process. It's a decent process. Let's take a look at the mechanism for the reaction. The reaction mechanism is going to involve HA. And you might say, well, I don't see any HA in this reaction. They didn't add HCl like that last example. And so what's all this HA coming from? Well, let's balance out the equation here, right? If you're replacing this over here, right? If you're substituting this for an oxygen and losing bromine and you're losing an H from there, guess what the byproduct is going to be? The second this reaction starts, you're going to start generating HBr. And by the end of the reaction, you're going to have 3 full equivalents of hydrobromic acid floating around. And in addition to this, the other byproduct that you get is phosphorus acid. There is no shortage of acid in this reaction. From the first bond you start making, you've got acid floating around. And it's hard to imagine conditions that are more acidic than this. So we already know what effect acid has on substitution rates. So guess what my first step is going to be? My first step here is going to be protonation of this PBr3, of this, that's the worst drawn arrow. Sorry. Let's go ahead and protonate that phosphorus atom. And when we protonate that phosphorus atom, we generate this phosphonium intermediate over here. And I just want to attack that phosphonium intermediate and make a 5th bond. Don't you want to make a 5th bond now that you understand phosphoranes? I do. And if I had a choice, I'd want to make a bond to oxygen. So let's go ahead and do that. We've got our alcohol floating around. We've got this super electrophilic, sweet-loving phosphonium ion there. And so we make a bond. I'm not going to show the deprotonation. We need a second step to pull this proton off, right? To pull the proton off that oxonium. I'm not going to show that. I'll just put 2 arrows here. Just because you don't need to see that. But now we've got our neutral phosphorane. Imagine in a second step we pulled off the proton. And now we can make something act as a leaving group. Phosphoranes aren't stable. Something wants to act as a leaving group. Let's go and draw, right? We've got our choice here. I'm not going to make H minus act as a leaving group. Now that I've made an oxygen phosphorus bond, I don't want to break that bond. That's the choicest bond in there. So let me make bromide act as a leaving group. And when I do that, I now have nucleophilic Br minus floating around in my reaction mixture. And so let's go ahead and use that bromide to act as a nucleophile. Now, I want to attack P+. That'll take us back. But, eventually, after you add into P+ 1,000 times, you'll get the idea that, maybe every once in a while it does this. We've seen that before. Oh, yeah. No, wait, hold on here. Let me, I don't want to draw P double bond O, directly go to that P double bond O resonance structure. Let me draw that arrow a little bit differently, just because it'll make it easier for us to see. I'm going to give the electrons to oxygen, and I'll choose to draw. I could have made it make P double bond O, but I just wanted to draw it as O minus because I want to explain how we get to the phosphorus acid with the OH on there. But yes, it's like P double bond O. And so now this oxygen is going to protonate, and that's how we make that OH group on the phosphorus acid byproduct. And notice how I call this phosphorus acid, not phosphoric acid. Phosphoric acid has P double bond O on there. Phosphorus acid is a reagent you'll never use or see people use. And so now that leaves us with this phosphonium ion intermediate here. I got to go quick because we're running out of time. And I'm just going to now deprotonate the phosphonium. I'm going to take the proton off the phosphorus. You see how that proton on the phosphorus activated this whole process from beginning to end, and then when you're done with the proton, you go ahead and remove it. There we go, it's gone from there. So we put that proton in the beginning, it facilitated all this substitution, and the last step we pull the proton back off. Now when we come back, we're going to talk about why this made DNA synthesis possible. Oligonucleotide synthesis, PCR primers. Without this chemistry, modern biotechnology would not exist.